Okay, good morning, everyone. Welcome to Friday. I hope your weeks have been pleasant and that your weekends have also been pleasant and restful. That's important. I know I need to sleep tomorrow. Yesterday, we at least began a cursory glance at the content of Chapter 3. Just going to continue that. Chapter 3 is not going to be a very long one. We'll definitely finish it by the end of next week. Before we get into that today, though, how y'all doing? And do you have any questions about anything? Okay. Well, you're all doing good. Stay that way. Rock to a flying start today. Okay. All right. So the Chapter 2 quiz and homework we did last night, and a lot of emails from people asking for help last night, which is good. It tells me that people were doing the assignment, and even if you're having trouble with it, I'd rather you do it and have trouble with it than not do it at all. Again, please email me anytime. I was at my computer till midnight anyway, so no issues there. Now, I remember, I didn't actually get around to posting the Chapter 3 quiz and homework last night. My apologies. The Chapter 3 assignments will tentatively be due not this coming Tuesday, but the one after that. We're definitely going to finish Chapter 3 next week, so Chapter 3 homework the week after that, Chapter 4 the week after that, and the first test, again, will be around the second week of October, I would say. Just to keep that in everyone's brain. Now, Chapter 3 itself, we've been talking, prior to beginning this, we were already talking about momentum and impulse. And yesterday we at least defined collisions. In a collision, there has to be force between two objects as they are in contact for some amount of time. Technically, even me pressing, just tapping and then pushing against this mouse is technically a collision because there is an amount of force for an amount of time. Also, an explosion counts as a collision because there's a certain amount of momentum on each of these objects, then all of a sudden there's a force on each of these objects for some amount of time while the explosion lasts. Explosions are related. Explosions do use the same math as the collisions that we're going to do. So they're kind of the same thing. And in collisions, since force is applied for an amount of time, and if the objects are going to accelerate, it means they're going to change velocity, change momentum. The change in momentum is defined as impulse. So every collision is going to involve force, time, change in momentum, and therefore impulse. Formulas up here are ones we've already had. This is still Newton's second law, just rearranged slightly, as shown yesterday. The new concept that we left off on is a concept is about something that happens during collisions. So, as an example, let's say that you have placed a target, just some object, couple of years, what my family would do for Thanksgiving is usually we would have cider or something, just apple cider, And afterwards, we take all the glass bottles, put them on the fence, and then we collect every BB gun we had access to and just try to shoot them off the fence. And surprisingly, the BB guns were able to shatter the glass. Now, when the BB strikes the target, we're going to have a collision. There's going to be some amount of force between those two objects for some amount of time. And the velocity of each object is going to change. Therefore, it's going to have a change in momentum and an impulse. Now, if your goal is to knock the target off of the fence post, you want to give it momentum. If it's going to begin moving, it's going to gain momentum in that situation, right? So it initially has none. It's going to begin moving, so it'll have some momentum. Meanwhile, what happens to the momentum of the BB? It's going to decrease. It will slow down, so its mass will stay the same, and its velocity will decrease. So the momentum of the BB will drop, and the momentum of the target will rise. Something of note with collisions, though, is if the BB loses, say, 10 kilogram meters per second of momentum, then this, my thermos should gain 10 kilogram meters per second of momentum. Momentum is kind of like energy in that you can't really destroy it. Energy can't be destroyed. It always just has to go somewhere. You do a physical activity, the energy you use up isn't gone, it's just turned into a different form. And since humans are warm-blooded, and since all friction creates thermal energy, the energy you use usually becomes heat, which is why you get all hot and sweaty after you exercise. So the energy isn't destroyed, it just takes on a different form. Meanwhile, momentum can't be destroyed, it just transfers what object has it. So, we have this principle called conservation of momentum, where the momentum in the system initially must be the same as the momentum in the system after the collision. You know what? Actually, I'm going to rewrite this a little bit. The version I'm putting on the board is better. Total momentum in a system initially is equal to the total momentum in a system. Total momentum in a system finally. All collisions have to have a before state and an after state. There's what everything is like the moment before impact, and then there's what everything is like after impact is done. In a moment, we're going to do a couple collision example questions, and all of those questions. This is my green marker. These are my favorite color. I don't appreciate that one going there. That's not the one I pick up. The initial side represents everything that is going on in the system of objects before they collide. The second side represents everything that's going on right after the collision is finished. And the exchange of momentum has completed, and contact has either ceased or the objects have begun moving at the same velocity after the collision, which, again, I'll show in a minute. So, in all collisions, every single kind of collision that we're going to show and talk about, and this does include explosions, total momentum initial equals total momentum final. It's called conservation of momentum. You're now going to demonstrate this. First, though, we left off on this last time. Does anyone have any questions about this principle? You've all definitely felt and observed this yourselves before. I said how baseball and golf are basically impulse to the game. And when you're playing those games, there is a collision between your sporting implement and the ball. And in that collision, momentum is going to exit the bat and enter the ball to send it off in its new direction. So that's one example, but the example I have prepped is one similar to the bottle on the fence. Instead, we have a chunk of wood on the fence, and you're throwing a shuriken at it. Does anyone not know what a throwing star is? The reason I went with this is because usually the point of a throwing star, if you're throwing it at a wooden target, is that it will stick into the target, which makes our math a lot easier if the two objects join after the fact. So, our example here, this is going to be our first collision example. You have a 100-gram throwing star, and you're just going to throw it at a piece of wood you have on a fence post. The throwing star has a mass of 100 grams. So I'm going to start listing the things we do and don't know over here. It's going to be important to list what object you're talking about, because we're going to have two objects that each have their own sets of mass and their own sets of velocities. So each unit is going to have a subscript telling you which it is, and I'm going to try to make that as legible as I can on the board. We've got mass of the star is 100 grams. And that star is thrown horizontally. So we've got velocity, star, initial, because this is before the collision happens. This is after you throw it, right before it's going to collide with the target. So velocity of the star initial is 25 meters per second. That star is going to strike a 16-kilogram piece of wood. So mass wood. Kilograms. If that piece of wood is sitting stationary on a fence, what is its initial velocity going to be? Very good. Stationary means not moving. Now, so this is everything we know about before the collision happens. When the collision commences, the star is going to stick into the wood, and typically, again, the goal of this sort of target practice is to knock your target off of the fence post. So, in this collision, we want the star to lose momentum and the wood to gain momentum, so that after they stick together, they are now both moving and the whole object falls off the fence. So, they're going to be moving at some other final velocity after the collision. We don't know what that is yet, and that's going to be what we're finding out. Any questions about the setup, the physical situation? Now, it always helps to draw a picture for all of our physics questions, and because collision questions always have a before state and an after state, it's especially helpful to draw both states. So, what I'm going to get in the habit of doing is putting this dotted line in between the two states. We have before, and we have after. It's been happening more and more recently. Is it just, do you think it's furniture moving, or do you think it's electrical feedback in a speaker system? Scientific method, we could design an experiment, but it doesn't seem like the best use of our time. So, we have our target, which I'm going to draw as a very cartoonish log. So, does that look enough like a log? Just a chunk of wood. That is a mass of 16 kilograms, which is actually very heavy. Its initial velocity is 0, so it is initially not moving, just sitting stationary. The star is going to approach it. star has a very low mass. Grams, and its initial velocity is 25 meters per second, which is a very good throwing arm, by the way. Well done. And then after the collision, two objects are going to stick together, so it's just physically stuck in the side now. They still have the same mass. Their masses are unchanged, but we now don't know the velocity that they are moving at together. So the same masses as before, those didn't change in the collision, but in this, it specifically says these objects are going to stick together. So they're now kind of functionally one object. If they're the same object, they're stuck together, they're moving together, that means they're going to be moving at the same final velocity, right? Which means when we set up our formula, since they're moving at the same VF, that's going to help simplify a few things. It's why I didn't specify the wood final or the star final. Since this problem says stuck together, it's the same answer, and that's going to help us. So, this is our physical system. Now we just need to start doing some math. Now again, we have our before state. You have to look at all of the momentum in the system before the collision and compare it to all of the momentum in the system after the collision. So, a lot of the same ink on the board now, so let's see if this red marker still has some ink in it. Yes, it does. I like putting different parts in different colors. I feel it helps us a little bit. So, we need to begin by looking at the total momentum in the system of each object before the collision. Now we have two objects, the star and the wood, so we need to look at and add up both of their momentums, which is going to look something like this. So there's two objects, momentum star initial plus momentum wood initial. The goal is to look at the total momentum in the system before the collision starts, and these are the two things that are present. We need to look at both of their momentums in conjunction. And then after the collision, we're going to do the same thing, but look at their momentums after the fact. So, what is our standard equation for just momentum of an object? Very good. So, we want mass of the star times the velocity of the star initial. That's going to tell us the star's initial velocity. Plus mass of the wood plus velocity of the wood initial equal to, and then afterwards, momentum of the star final, we want mass of the star, which doesn't change from beginning to end, so that's going to be just the same number as before. Mass of the star, I know my font is getting a little smaller here to make everything fit, I'm sorry. Does everyone understand the meaning and the placement of each of these? Does anyone not understand the meaning and the placement of each of these? Like that. Okay. So mass of the star times the final velocity, because it went from this speed down to this unknown final speed, and same with the wood. these types of questions are going to involve a lot of the momentum formula repeated over and over and over again. Because you have to look at it for every single object in both sides. But in a second, we'll plug in some numbers and it won't look so samey. So, we got our formula set up. Let's start plugging in the things that we know. Mass of the star is 100 grams. What should we do to this number first? Very good. We want kilograms. All of our formulas take kilograms, and 100 grams is 0.1 kilograms. So 0.1 is the mass. The velocity is 25. Now, what's the momentum of the wood before the collision? It's 0. It has mass, but its initial velocity is 0. I will go ahead and put it up here, 16 times 0, but that's just going to become 0, and that term is just going to go away. Now on the final side, we have mass of the star again, so 0.1 times its final velocity, plus mass of the wood times its final velocity. Now notice again, since we've specified that they are going to stick together, it's the same VF, it's the same variable, meaning we can simplify that side to help us solve for just VF. So, I'll take it down to the next line of algebra. 0.1 times 25 is just going to give us 2.5. This is 0, so it's just going to go away. So 25 equal to, we have here 0.1 times VF plus 16 times VF. What math rule can we utilize to try to simplify this and just help us start getting VF by itself? We can add them together. You could okay, so good answer. So the two things we could do here is add the two together, which should give us 16.1 times VF. You could also use the distributive property, make it 0.1 plus 16 parentheses, whole thing times VF, but that's still going to get you to the same point. And this sort of symbolizes the fact that since they're one object, their masses would logically add together. They're stuck together as one unit, all of their mass is moving together at this velocity, and the sum of their mass is 16.1 kilograms. So now all we have to do is divide the 16.1 over, and so velocity final should be equal to 25 over 16.1. That should be about, thank you very much. Say that again.
0.16.
0.16?
Should be 2.5.
Yes. Well, it should be at least 2 point something.
In the equation, it's 2.5.
Oh, no wonder. Thank you, thank you. It's still early for me. Thank you very much. You said it was 0.16? Okay, sorry about that. Now my desk is in the way. Can everyone see this? Thank you. 2.5 divided by 16.1 gives us 0.16 meters per second, which is not very fast, but it's fast enough to knock something off of a fence post. So, congratulations, you have accomplished, we have accomplished our objective. And that is your first collision example. Any questions about this question specifically? Okay. Now, I'm going to call a quick break. This is a good time if you need water in the bathroom, because I want to go find something in this closet that will help demonstrate where we take this next, also on Thursday. And I'm out of water. So, the question we just did, sorry, is an example of one type of collision. The throwing star stuck into the wood, and as a result, they began traveling as one object. Now, from your own experience, in all collisions you have witnessed, do the objects always stick together? No. In this particular case, it makes sense for them to. The throwing star has a sharp edge, it's going to stick into the wood, so logically they would travel together as one object. But what other types of collisions have you witnessed? Okay, so plenty of objects, instead of sticking to whatever they hit, will bounce off of it. And I have this plethora of throwables here to demonstrate the differences between some of these types of objects and collisions. So the first pair that I'm going to directly contrast to one another, this is a ping pong ball, and this is just a wad of styrofoam. They are about the same size, about the same mass, so really the only major difference between them, as far as we're concerned today, is what they're made of. And what they are made of is going to have a tangible effect on what they do in a collision. So, the first thing I'm going to do is I'm going to cause a collision by throwing this at the wall. So, everyone watching? And this should be plenty entertaining because I was very bad at all sports that involve throwing. Okay, so it did bounce off. But what do you think this is going to do? Okay. If I hit anyone, I hope it's me and not any of you. I'm strangely impressed by that. Yes, it was a lot of momentum. Very good. So, what's the major difference between the two things that just happened? Okay, one bounced more than the other. Now, both of these objects have about the same mass, and I threw them, so they should have been moving at about the same velocity. So before the collision, they should have both had roughly the same amount of momentum, right? Same mass, same velocity. They went into the collision with the same amount of momentum. Additionally, when you compare momentum to a similar principle now, they both should have gone into the collision with the same amount of kinetic energy. Remember this formula? Kinetic energy is the energy of movement. And whenever you make something move, you are simultaneously giving it momentum and kinetic energy at the same time. These are both different aspects of movement that we can use to measure how an object is moving using that. So a moving object has both. It's not one or the other. They're both happening at the same time. And because the objects I threw have about the same mass and the same velocity, they should have been approaching the wall with the same momentum and the same kinetic energy. Meaning they were bringing the same amount of stuff into the collision, and they were both hitting the same immovable wall. Excuse me. And yet they both reacted differently upon striking it. The objects are made of two different types of things, and those types of things, the styrofoam versus the ping pong ball, create different types of collisions. There are two different kinds. There is elastic collisions, and there are inelastic collisions. I realize that those two words are incredibly similar except for the IN part, and I need to be very specific when I say an elastic versus an inelastic. So I'm going to try to enunciate those properly each time. These are the two major types of collisions. Every collision can be described as more elastic or more inelastic in how it works. The example we just did with throwing star in the wood is an example of an inelastic collision because the two objects did not bounce off of each other. If one object bounces off of the other, that means that the collision is at least some kind of elastic. But if it's inelastic, if an object is completely inelastic, then it will not bounce. The objects will just stick together and move as one. Now, I don't really have a very good object to demonstrate a perfectly inelastic collision for you guys because most objects bounce a little bit. Like anything you've ever dropped on the floor probably bounced a little bit upon impact, right? So in real life, most collisions are a little bit of both of these types. It is possible to create a perfectly inelastic collision, usually if you physically force the two objects to stick together. I'm wondering though. Just curious to see what type of collision this thing forms. Ooh. Sorry, I should have warned you. I apologize. So that was even more inelastic than the styrofoam ball. That mostly just dropped off of the wall. A perfectly inelastic collision, if I had some Play-Doh or clay or something, that would probably just warp and stick to the wall, right? So, I need to make some room on the board. Of course I don't have my eraser, I just threw it. Okay. All right, so we've got inelastic and elastic. We're going to compare the types of collisions and the types of objects that create each type of collision. And this marker needs a break. Okay, so again, the shuriken in the wood is an inelastic example. We knew this because the two objects stuck together. So, in your notes, I recommend writing the same columns as here so that you can show what traits belong to each. In an inelastic collision, things tend to stick together. Conversely, in an elastic collision, they will bounce off of each other. So again, in real life, most collisions exhibit a little bit of each. Again, I can drop anything on the floor, it'll bounce a tiny bit. So we're mostly going to generalize in terms of how a collision mostly performs. So in general, if the two objects don't bounce off of one another in a measurable way, we're going to consider them to be inelastic. So if they stick together, we're going to say it's inelastic. If they bounce off, it's elastic. There are certain physical traits of an object that will determine what it will do in this type of a situation. Again, where'd they go? The first two balls that I threw, the styrofoam and the ping pong ball, are made of different things. And it's their physical composition that's going to determine what type of collision that they will have. Styrofoam, if I was to crush this, it would just disintegrate. It would crush into a smaller shape and then stay that way, right? Meanwhile, if I press inwards on this ping pong ball and I release it, what's going to happen? As long as I'm not being too hard on it, as long as I don't break it, it will tend to go back to normal. That means that this ping pong ball, like a super bouncy ball or anything made of rubber for the most part, is exhibiting elastic tendencies. And I'm going to put a different definition of it. Okay, yeah, this will be fine. An elastic object, an object that is defined as being elastic, is one that will deform and then go back to normal. When I crush the ping pong ball, as long as I don't break it, it will go back to normal. Doing it right now. So when I deform it, and deformation is defined as, physically pushing on an object to change its shape. So I change its shape by pressing it inwards, and an elastic object, all by itself, will press itself back to its original state and then eject itself from my hand because I lack all coordination. So again, it deforms and then goes back to normal all by itself. That is an elastic object. Anything that bounces does this. Every time an object bounces, it technically deforms by some amount and then springs back to normal. And that springing motion, the act of, where'd it go? The act of sort of righting itself, as this little piece here springs back out, it's going to exert a force against the surface it's bouncing on. It's going to act literally like a spring and propel itself off of whatever it just hit. Every elastic bouncing object will do this. I know what, this might be a little easier to see. This ball is not styrofoam, it's the bouncy flexible foam. And when I press in on it, what's it going to do when I release it? It goes back to its original shape. So whenever a super bouncy ball, a tennis ball, a basketball hits the floor, in the moment it hits the ground, it deforms. If you had a freeze frame camera and you were watching a game of basketball, you could see this happening. And a moment later, you would see it go back to its normal shape as it sprung off the floor. Again, as it goes back to normal, it literally pushes off of the floor, and that's why it bounces. Meanwhile, an inelastic object, like the styrofoam, if I was to press in and crush this, it would stay that way. This kind of foam lacks elastic tendencies. That makes it an inelastic object. It's a kind of object that will deform and then stay that way. So any object that doesn't bounce deforms and then does not go back to normal. Because it doesn't go back to normal, that motion doesn't spring it off whatever it just hit. So it just doesn't bounce off. If I had, I'm going to try to see if I can find some to bring to class next time. If I had like Play-Doh or a wad of molding clay, and I threw that against the wall, it would deform into a pretty flat shape upon hitting the wall, and then does clay or Play-Doh revert back on itself. It's just going to stay in that shape and probably stick to the wall. So that's probably one of the most inelastic collisions I could show you, because most things are at least kind of elastic. It's hard to see this thing deform on impact, but technically it does to some degree. Pretty much anything that bounces even a tiny bit will. And so those are the two major types of collisions, elastic and inelastic. Mechanically, this is caused by the different types of objects involved in the collision. And mathematically, what we're going to be observing and doing work on is the difference in what happens to energy involved in these collisions. Momentum is always conserved in every single type of a collision, because momentum can only exist as momentum. We can't really destroy momentum. It has to go somewhere. And it can only exist in one state. So it's constantly being transferred back and forth between objects as momentum. But again, if an object is moving, it also has kinetic energy. And energy can take lots of different forms. It can take kinetic, it can take gravitational potential, it can be chemical, it can be electrical, and actually some energy can take the form of sound. You don't usually think of it like this, but sound is just a ripple in the air. When I speak, I create vibration in the air by giving energy to the air. And if the energy is in the air, it's not in whatever object originally had it. Technically, I'm burning calories just talking. So anytime a collision is loud and doesn't go back to normal, it has burned off a lot of kinetic energy in that collision. Momentum was still conserved because it has to be. Momentum is always conserved. But in an inelastic collision, where things tend to be loud and noisy and where objects deform and then stay that way, you lose kinetic energy in the collision. It goes into other forms because energy can exist in other forms. Usually it'll go into heat because all friction just turns energy into heat. But the inelastic collisions also tend to be louder, like a car crash, or if I was to throw Play-Doh at the wall, that'd make a really weird noise. Energy gets wasted in these types of collisions, and it ends up making everything slower. These types of collisions, the non-bouncy ones, tend to be slower as a result. They're not really as exciting. That, however, does make them safer. Car crashes are meant, like, car manufacturers need to account for what happens if this vehicle is in a crash, and so they design the bumpers of their car to be inelastic and compress and not go back to normal, so that you lose energy in a car crash and you don't keep it and keep moving, which is more dangerous, which is what we're going to talk about next time. I got kind of excited talking about this. We're showing that person on the end of it, talking about Phys1000 Friday. So, Chapter 3 homework and quiz will be going live shortly. You begin looking at them. We'll finish Chapter 3 pretty quickly next week. Let me, again, any questions you have about anything over the weekend, if you don't have any questions for me now, I do hope you all have a wonderful weekend. Thank you, and see you Tuesday. It's listed under Lab 4, and this particular assignment, like the actual document is going to be the same as the one that was done in person. So it's listed, it should still say Physics Lab Online Lab 4, tension and Newton's third law, and at various points where you would measure something, talk to me and I will send you the data that you can use instead.
Well, I'm going to do it probably after my lunch, so it'll be
okay.
So.
All right.
Thank you.
You're welcome.